Let me start by introducing the speaker today. I'm very glad to present Mark Alford from Washington University in St. Louis. I always have a tendency to mix two universities. So it's Washington University in St. Louis. He got his PhD in 1990 at Harvard University with the thesis advisor Sidney Coleman. He had several postdoc positions at the University of California, Santa Barbara with Professor Anthony Z, then at Cornell University with Lepage. He became a member of the Institute for Advanced Studies in 95 through 98. Between 98 and 2000, he was a research scientist at Massachusetts Institute of Technology. He got a faculty position at the University of Glasgow in 2000. In 2003, he moved to Washington University in St. Louis, and he was there since then. Since 2012, he is a chairman of the physics department at Washington University in St. Louis, and he works on many different things. He started from lattice QCD. He worked a lot on color superconductivities. He works in interdisciplinary fields, astrophysics, dense matter, nuclear physics. So it's actually a wide spectrum of things he joins in his research. Without any further ado, I will give the microphone to Mark.
Okay. Thank you very much. Thank you for that very nice introduction. Thank you for inviting me to give one of these online colloquia. So as you see, I'm going to be talking about transport and dissipation in neutron star mergers. And what I'm going to be talking about is based on a series of papers with the Frankfurt group and my former postdoc Kai Schwenzer, and with Arus Harutunian and Armen Sadrakian, and with my current student Stephen Harris. And ultimately, there's a video that if you click on this in the PDF, it'll take you to YouTube, and you'll get to see a sort of cartoon version of what I'm talking about today. And of course, the money comes from the US Department of Energy. Okay, so the outline of the talk is firstly, the general idea, neutron star mergers as a probe of dense matter. And the idea is that there are different phases of dense matter, we think, and people often try and think about the equation of state, and that's an important thing. But in general, in condensed matter, you may have better luck distinguishing phases by their transport properties than you do by their equation of state. For example, a superconductor, when it becomes superconducting, its compressibility may not change that much, but its electrical conductivity changes dramatically. So we're trying to apply the same idea here. And the things I'm going to talk about are, firstly, I'll talk a little bit about thermal conductivity. Is it possible that thermal conductivity plays an important role in neutron star mergers? And for that, you look at the damping time for temperature inhomogeneities, and you ask, do they damp out? Is thermal conductivity operating fast enough to influence the evolution of the merger? And then I'll talk about the similar analogous question for bulk viscosity. What is the damping time for density oscillations? Those are the things that are damped by bulk viscosity. And we'll be asking, does that happen fast enough to be relevant to the evolution of mergers? And then at the end, I'll have some forward-looking thoughts. So let's start with mergers as a probe of dense matter. And of course, we have to start with the map, the famous, largely conjectured phase diagram of QCD, which has some definite things in it, like there's the vacuum to nuclear matter transition, which we know about because we see nuclei, and we think there's a critical endpoint for that. We believe there's a chiral line with an endpoint, and heavy ion collisions look for that at high temperature. Neutron stars probe the low temperature and nuclear density up to whatever the density of the center is, which may take you into some form of non-nuclear matter, may take you into quark matter, we don't know. And I'm going to talk about mergers today because mergers probe an interesting new area of the phase diagram, which is this sort of nuclear density, and you might call it warm dense matter, temperatures that go up into the tens of MeV, which is certainly not achieved in isolated neutron stars. Okay, so a little bit more about neutron star mergers. As I just said, they probe things at densities up to the central density of a neutron star and temperatures, according to the simulations, up to tens of MeV, maybe 60 MeV, maybe higher. This is a frame from a simulation by the Rosola group at Frankfurt. I'm not going to try and play the video here, but these contours show you different densities, and you can see there's a lot of craziness going on here. These two stars have just joined. It's got a sort of double lobed structure, and these little dots here, we'll come back to them later on, they are co-moving fluid elements, and you can see here they're moving in all different directions, which tells you there's a lot of inhomogeneity, there's compression, there's shear, there's all sorts of stuff going on. And obviously, if we want to use these mergers as probes of dense matter, and we want to find out if they can give us signatures of the presence of different phases of dense matter, then we need to include all the relevant physics in the simulation. We need to include the equation of state, but we may also need to include other physics as well. That's one of the main themes here. So here's another presentation of how the range of conditions in a neutron star merger looks. This one was produced by Matthias Hanauska, also from the Rosola group in Frankfurt. And this first frame is temperature up the side, density in units of nuclear saturation density along the bottom, at about 2 milliseconds after the neutron stars touched. And the second frame is a little later, about 10 milliseconds after they touched. And what you see in this first frame here is that the material in the merger covers quite a range of densities and temperatures. It goes up to 3.5 times nuclear density. The details depend on the equation of state that was used in the simulation. And there's a lot of variation in temperature, going up to around 60 MeV in this case. The color coding tells you where that material was. So the purple is near the center at small radius. And then as we go down the spectrum to blue and then green and then orange and red, we're going outwards to the outer parts of the merger. So it's not too surprising. The middle parts are the densest, the outer parts are the least dense, but there's a lot of range of density and temperature here. Later on, about 10 milliseconds in, you see things have settled down a little bit. There's still a range. You get this interesting sort of mountain or arch shape where you see the densest parts at the lowest radius are not that hot, and the outer parts at a high radius are not that hot. The outer parts are low density, the inner parts are high density. And in the middle, there's a region. This is an equatorial slice, so this is actually sort of a toroidal region where it's the hottest. Now, I'm not going to get into details of neutron star mergers. That simulating them is not my business. What I'm going to use this as motivation for is the relevance of transport properties. So what we see in these presentations of the results of simulations is that you've got a lot of variation. You've got the temperature varying from place to place in the merger. And if you've got variations in temperature, you start asking, do we have thermal conductivity playing an important role? As you saw in the previous slide with the little fluid elements going in different directions, you have variation in fluid flow velocity. And that means you have to ask about shear viscosity between flows that are not going at the same speed. And finally, you have temporal variation in density. The density is changing. And then you start asking about bulk viscosity. If we're compressing and uncompressing the material, you can lose energy through bulk viscosity. So the point of this introduction is that the neutron star merger is a very dynamic environment with a lot of sort of exciting, crazy, time-dependent stuff going on. And that makes us wonder which kinds of transport and dissipative properties of the material do we need to include alongside the equation of state in order to correctly capture the behavior of the material. All right, so the one number that you need to bear in mind in this whole thing is for how long is there exciting, highly position and time-dependent stuff going on in the merger, and that's roughly 20 milliseconds. So what you're looking at is, are there dissipation mechanisms like thermal conductivity, shear viscosity, bulk viscosity, whose equilibration time, in other words, the time it takes for them to have an impact on the dynamics, is less than or of order 20 milliseconds. If they operate that quickly, then they can affect the merger. If they operate more slowly than that, then the merger is, the exciting part at least, is over and done with. The exciting part from the point of view of these inhomogeneities is over and done with, and they're less likely to be influential. So we're looking for dissipation mechanisms that are strong enough that they operate, have an influence on the 20 millisecond or faster timescale. So here's the executive summary, because I realize at some point you may be called away by urgent other commitments from this talk. So the summary right up front is, with thermal equilibration, it may be fast enough to play a role in a merger if neutrinos are trapped and if there are short distance temperature gradients. And I'll show you, I'll flesh that out a little bit more in the next part of the talk, but that's going to be the conclusion. Shear viscosity, I'm not going to talk about. It has a similar conclusion. And then bulk viscosity, which I will talk about in the second part of the talk, the results that we found indicate that bulk viscosity could damp density oscillations on this 20 millisecond timescale. And we think there's good reason to include bulk viscosity in merger simulations for that reason. Okay, so that's the big picture, the conclusion we'll be working towards. So let's start with the first transport property that I want to say a few words about, and that's thermal equilibration in neutron star mergers. So here's the basic setup. We imagine just a hot region, hotter than its surroundings, and we ask how long does it take to cool down to the same temperature as its surroundings via thermal conductivity. So we've got this hot region, little picture here. It's delta T hotter than its surroundings. It's got a size Z typical. It's the distance over which the temperature goes from the hot in the middle to the ambient temperature around the outside. So this little hot region has some volume, which is the Z cubed. It has some surface area. We're doing a rough estimate here, so you can imagine it like a cube and say it's 6Z squared, or you can use some pies if you want to have something that's a more rounded shape. Doesn't really matter too much. The big question then is, how long does it take for this hot region to have the heat conducted out of it by thermal conductivity, and for it to equilibrate back to the same temperature its surroundings? And this time scale, this equilibration time scale, we can estimate it very simply by saying how much extra heat is there in this hot region, and divide that by how quickly does the heat flow out of the hot region. And if we have how much there is divided by how fast we lose it, that's going to give us the time scale on which this hot region relaxes to the ambient temperature. And again, the 20 millisecond time scale is always in the back of our minds. Thermal diffusion, thermal conductivity will be important if this time scale is faster than 20 milliseconds, thereabouts. Okay, so let's try and estimate these things. So the extra heat in the region, that's just the specific heat of the nuclear matter times the volume times the extra temperature in there. And so it's the specific heat times the volume times the extra temperature. The rate at which heat flows out, that's the thermal conductivity times the temperature gradient times the area. And if we go back, we can, the area is this rough Z squared quantity. The thermal gradient, if it's a sort of smoothish hot region, is about the extra temperature divided by the size of the region. So we roughly estimate the temperature gradient as delta T over the size. And so now we have our estimate of the rate at which heat leaves the region through thermal conductivity. So the time it takes, the characteristic time scale for this hot region to cool down, amount of energy stored divided by rate at which it leaks out. We divide these things, delta T cancels, and we find that it has this form. It's a fairly understandable form. The specific heat capacity is on the top because the more heat there is stored in the region, the longer it would take for it to lose its heat. the
Mark, we have
thermal
a question.
conductivity. Sorry.
We have a question.
Okay.
Go ahead.
I want to ask a question about this, the previous slide.
Okay.
That you have a temperature, a well-defined temperature here, and I mean, if you are actually assuming that there's equilibrium here, yeah?
Well, we're out of equilibrium. There's a local equilibrium. You know, in this region here, it's locally equilibrated to a temperature, and over here, it's locally equilibrated to a different temperature, and we're asking how long it takes.
But how do you assume that there's a local equilibrium here?
Well, because thermal
reasoning?
equilibration is done by the strong interaction locally, and the strong interaction is capable of doing that quite quickly.
Thanks.
Okay. Okay. So yes. So how long it takes to equilibrate? Specific heat on the top, because that tells you how much heat is stored, and the thermal conductivity is on the bottom. Obviously, the higher the thermal conductivity, the faster the heat leaks out, and so the shorter the equilibration time. And the size of the region is important because of this sort of scaling issue that the amount of heat stored goes like z cubed, and the rate at which it leaks out scales differently because it's to do with the surface area and the gradient. So small regions equilibrate faster. Not surprisingly, they've got more surface per volume, if you like. So if we want to calculate or estimate the thermal equilibration time, the things we need are the specific heat capacity and the thermal conductivity. I'm just going to quickly show you in rough terms how we estimate those and show you what we get at the end. So for this, we need to start looking at the actual microscopic physics. You know, what have we got in this neutron star? And we're going to take the generic hypothesis of ordinary nuclear matter. So there's neutrons, protons, electrons, and maybe neutrinos. And what I'm showing you here are the Fermi surfaces in momentum space. So here the neutrons, they are 90% of the baryons, and they have a Fermi momentum of about 350 MeV, so that's the radius of this sphere. The protons are about 10% of the baryons. They have a smaller Fermi sphere in momentum space, about 150 MeV Fermi momentum. The electrons, they have the same density as the protons because it's electrically neutral. And the neutrinos depends on their mean free path. If things are hot enough, their mean free path becomes short enough that they get trapped, and then you may develop a Fermi surface of neutrinos as well. So those are the players we have in the game. Those are the species that are available to do the things that we're interested in: store heat, transport heat, and so on. So with that in mind, let's ask ourselves about the first thing, the specific heat capacity. So the specific heat capacity is given by how many states there are available to carry energy that's of the order of the temperature, which is the volume of momentum space with states available. And if you look at the different species we have available, where is there a bunch of states that can be accessed by dumping in a little bit of energy into the system? Mostly it's the neutron Fermi surface. There's a lot of phase space here where you can dump in a little bit of energy and excite a neutron from a state just below the Fermi surface to a state just above the Fermi surface. So roughly speaking, the specific heat is given by the surface area of the neutron Fermi surface, which goes like it's Fermi momentum squared, times the thickness. How much phase space is there in this thermally blurred surface of the neutron Fermi surface? So, okay, we can look at that. This is the energy momentum dispersion relation for neutrons or protons, and they're sort of non-relativistic. So, you know, their energy is looking like p squared over 2m and then gradually becoming more relativistic. So the blurring of the Fermi surface in energy is given by the temperature, but we want to know what's the range of momenta that makes available for storing energy. And that's this delta P. And there's a simple scaling from the temperature, the energy blurring, to delta P, the momentum blurring, through the slope of the dispersion relation, which is the Fermi velocity, which is the Fermi momentum divided by the effective mass. So the amount of phase space, the thickness of the Fermi surface is the temperature divided by the Fermi velocity, which is this. So we then just plug that in. We've got our surface area times thickness. That's how much phase space is available to store heat. We put in the Fermi velocity. We get some cancellation of powers of the Fermi momentum of the neutrons. We end up with something that goes like the temperature, the Fermi momentum, and the effective mass. And the Fermi momentum is just the cube root of the density. So when you put in the numbers and the pi's and everything, you end up with the specific heat going like basically the density to the 1/3 times the temperature. So that's a pretty straightforward, robust estimate you can make of the specific heat capacity of regular nuclear matter. So now we go on to the other component that was in the numerator. That's how much, telling you how much energy is stored. Now we want to ask ourselves how quickly it leaks out, because we want to get that equilibration time. So the other thing we want to estimate is the thermal conductivity. So thermal conductivities in general look like the density of the particles. Obviously, the more particles there are, the better they are at carrying heat from one place to another. How fast they're going. All these particles tend to be going at some non-negligible fraction of the speed of light. And the mean free path. Something with a long mean free path can carry heat a long way more easily than something that's running around doing a random walk with very small steps. So the thermal conductivity will be dominated by the species that has the right combination of having a reasonably high density, there's a good number of them, and a long mean free path. They can carry heat a long distance and they don't keep getting interrupted and sort of confined. So let's go through our various players here and ask who is going to be the dominant carrier of heat from one place to another. So what about the neutrons? Well, there's a very high density of neutrons. They're good for that, but they feel the strong interaction. And since they feel the strong interaction, they're going to have a short mean free path. They'll be interacting with their neighbors strongly. They won't travel very far before they bump into something. So they dominated the specific heat, but they don't seem like a good candidate to dominate the thermal conductivity. All right. What about the protons? Well, the protons, they don't have such a high density, and they're strongly interacting. So they're really no help at all if you want to move heat from one place to another diffusively. What about the electrons? Well, the electrons look more promising because the electrons, they don't have a very high density, but they also don't have the strong interaction. They only have electromagnetic interactions. So that means they can travel further before they have an interaction with something like a proton. So they look like they could be potentially useful for carrying heat around the place. And finally, what about the neutrinos? Well, the neutrinos present an interestingly complicated situation because it depends whether they're trapped or not. If the temperature is on the low side, so that the neutrinos have a very long mean free path, it's bigger than the size of the merger region. And so the neutrinos just escape. So there aren't any of them, right? There's no equilibrated population. There's no Fermi surface of neutrinos. So they are just escaping straight out of there, and they're not going to contribute to diffusive thermal conductivity. Now, I want to be clear, they may be contributing to heat loss. It's radiative, right? So they could be contributing to radiative heat loss. So this doesn't mean we should ignore them if we're interested in the fate of the heat in our merger. But for what I'm talking about right here, I'm talking about thermal conduction. And for that purpose, they're not really doing anything at all if their mean free path is too long. If the temperature is above something in the 5 MeV range, then their mean free path is smaller than the merger region, and then they are ideal for thermal conductivity because they have a long mean free path, and there's a population of them. So in this high temperature regime where neutrinos are trapped, it looks like they are going to be the guys that dominate thermal conductivity.
Mark?
Yes.
Quick clarifying question. What about phonons?
What about?
Phonons.
So there aren't, so this is certainly not a superfluid, right? It's much too hot for that. It's not superfluid phonons. And other phonons, I'm guessing there's nothing particularly to make them interact on long distance scales. Like, in the case of the neutrinos, their mean free path is going to be it can be, meters, hundreds of meters, kilometers. Phonons are excitations of the strongly interacting baryon density. And so my guess is that they will interact on a correspondingly shorter distance scale. Okay. So the neutrinos are looking like the guys.
I'm sorry.
Who can, yeah.
I'm sorry. I didn't notice that there was another question. If this is okay.
Yeah.
Hi, Mark. I have a question. You are not considering the superfluid state for the neutrons because the temperature that you are interested is higher than the critical temperature for that?
Yes, that's right. So in mergers, I mean, I could go back a few slides if you wanted, but maybe you remember that the typical temperatures that these simulations indicate are 1 MeV and above, quite a bit above sometimes. And the typical critical temperatures for neutron superfluidity are below an MeV. So we don't expect neutron superfluidity in this environment.
Okay, thank you.
Okay, so Igor, how are we doing?
Yeah, go ahead.
Okay, so so the neutrinos are probably doing the dominant job of carrying, diffusively carrying energy. So here is the answer for the thermal equilibration time. Remember, it has the specific heat in the top and the thermal conductivity in the bottom, and went like the size of the region squared. The neutrino-dominated thermal conductivity, I'm not going to go through it, but it looks like this. The thing I want to draw your attention to is that you've got the weak interaction coupling, the Fermi coupling in this case, in the denominator, in the bottom. And that's typical of transport properties. Transport properties usually have a coupling in the denominator. And as the interaction gets weaker, the mean free path gets longer, and the transport coefficient diverges. And that's exactly, it sounds a bit counterintuitive, how can the transport diverge in the limit that something decouples? That sounds weird. But we already saw how it works with the neutrinos, that what I just said about it goes like 1 over the coupling is true as long as the mean free path is smaller than the size of the system. If the coupling gets too small, the mean free path becomes bigger than the size of the system, and then it's not contributing to diffusive transport. So it's an order of limits. There are many situations in physics, interesting situations, where order of limits plays a role, and this is one of them. There's an order of limits between the size of the system going to infinity and the coupling going to 0. So in this case, we've chosen the regime where it still looks like 1 over the coupling. So we've got this thermal conductivity, which we can estimate based on the interaction of neutrinos with, say, electrons. And we can plug in this expression into our equilibration time, and we get this, which I've shown you in a sort of scaled form. There's a bunch of things that I in gray here because they tend to be of order 1, but the overall time scale that you get is about a second. When you put in the numbers, you find thermal equilibration time scale is about a second. It's got a factor of the temperature, which we think is going to be in the, above 5 MeV range. So this factor is not going to be huge. But this, remember, we had this size of region squared from the very beginning. And that appears to be the most important determinant of whether neutrino-dominated thermal equilibration is going to play a role. Because if you have small scale temperature gradients, like 100 meters or something like that, then this is a factor of 1/10 that gets squared, and that can pull your 700 milliseconds down to 7 milliseconds, and then it's in the interesting regime, the less than or of order 20 millisecond regime, where it could affect the evolution of the merger. So the conclusion with thermal equilibration is that if it's hot enough to trap the neutrinos and there's fine enough scale thermal gradients, then maybe thermal conductivity via neutrinos may be playing an important role in a merger. Okay, that's it for the thermal equilibration part. I'm going to go on to bulk viscosity now. If anybody wants to ask a question, I'm ready for that.
Well, if you insist, I want to return to the phonons. The thing is the dissipation will be controlled by the bulk viscosity that you are probably going to, not by the strong interactions. So in fact, the mean free path might be large.
Okay, I'm not going to try and address that right now. It's a thought. I mean, I don't think there are going to be enough of them to, there isn't a whole Fermi surface worth.
The density is T cubed. That's where you are absolutely right.
Right. Whereas the neutrinos will have a higher density. So.
Yeah. May I comment on that?
Go ahead.
So yeah, I think the phonon exists only for very long wavelength, which is much larger than the mean free path, and so they are few. I would guess that there are too few of them. It's not T cube. There is no phonon with such a short wavelength.
Are you saying that there are so many inhomogeneities that the phonons will not have a chance to develop?
No. I'm just saying that the phonon exists as a quasi-particle only if the wavelength is larger than the mean free path of other types of particles. Because phonon itself is a collective excitation.
So it doesn't have to do anything with the neutrinos, which have the longest mean free path. So they could easily compete with neutrinos.
Yeah, but this T cube would kill them.
That's true.
I think it's difficult for there to be enough of them to compete.
Right.
But okay.
Okay, I see two other people trying to ask questions. Go ahead, Qingyang, one.
Yes, I mean, Mark, you talk about the temperature dependence of the mean free path, but maybe I missed. Does the energy transfer per scattering depend on also the temperature?
Yeah, so this sort of kinetic theory formula here is a bit of a simplification. I was just trying to use it to give, the broad picture that which species is going to be most important. But obviously, when you calculate this thermal conductivity, you integrate over all different kinds of collisions, ones that deliver a big energy kick and ones that deliver a small one.
And that will have some temperature dependence, I assume.
Sure.
I'm just wondering, what is the temperature dependence?
Well, it's right here.
Oh, okay. So that involves both the energy transfer and the mean free path. I mean,
mean free path is a simplifying concept. When you calculate this thing, you don't calculate it this way. This was meant to help.
Okay, I understand. So that's the final result. Okay, yeah. Sure.
Yeah, this is the final result, which is calculated by other people, and that we cited them in the papers that we're talking about.
Yeah, no, I'm just wondering which one is more important. I mean, the mean free path, and then the energy transfer.
Yeah, no, this is a full proper calculation. This comes from a full proper calculation. The previous slide was to help guide your physical intuition about it.
Okay, thanks. Yeah.
Okay, Stanislav.
We have discussed plasmons, phonons, but then what about plasmons, which are driven by electromagnetic interaction, and then presumably their dissipation can be important here?
Well, my guess again is that they're bosons and they'll have a rather small density.
And they also have a large gap, so their distribution will be suppressed by that a lot.
Right.
Okay, one more from Sanjay.
Yeah.
Hi, Mark. Has anybody looked at the role of convection?
So convection, that's a macroscopic thing. So I would expect that to be captured in the dynamics of the simulation. And so I'm trying to do microscopic stuff here. Now, admittedly, I'm talking about mean free paths that get kind of long. So I maybe am blurring the macroscopic distinction somewhat. But I would expect that to be more a thing that emerges from the fluid dynamics of the merger simulation.
Yeah, do the simulations suggest that there's convective heat transport?
I don't know. We'd have to ask a merger. I mean, it may be hard to define because what you have is a big slosh, right, with a whole bunch of crazy stuff going around in circles, pulled by gravity, pushed by its angular momentum. It's an interesting question how you would pull out the convective component in that.
Yeah,
presumably turbulent.
Well, it may be turbulent, and that's why there may be a good chance of small distance gradients, actually, is because if it's turbulent, that can very well happen. But yeah, convective would be another mechanism that you need to think about, especially if it,
that happens in core collapse supernovae, where you generate similar ambient conditions.
Right. Yeah, certainly I'm not saying that this would be the only mechanism. I'm just saying, you know, is it non-negligible?
Okay, I think we started to make it like a question sessions, but one more and that's it. Okay, Manoush?
Yeah, thanks. Excuse me, you mentioned electron as a possible candidate to thermal conductivity. What about its contribution?
Yeah, so that's a very reasonable question. Yeah, because I put a green tick next to it here, and then I sort of abandoned it. If you do the same calculation with electrons, you get a similar looking expression, but the time scale in front here is more like 1,000,000 seconds or something like that. So
okay, thank you.
And that's because electromagnetism is not so much weaker than the strong interaction, whereas the weak interaction is a lot weaker, right? With the weak interaction, you've got, you know, hundreds of GeV scales down in here that really suppress the weak interaction and lengthen the mean free path of the neutrinos, whereas the electrons are just like, you know, the fine structure constant is only 1/100th, so they're weaker but not weak enough.
Okay, thanks.
Okay, please continue.
All right, so let's see if I manage to get anywhere with bulk viscosity in the time available. So the next thing I want to talk about is a different thing, the damping of density oscillations. So that's bulk viscosity. It's like sound attenuation if you're talking about regular sort of things in condensed matter physics on Earth. So the first question is, are there density oscillations? And here I'm showing a plot of density versus time for those little tracers that you saw in the first picture I showed of a merger. There were these little sort of tadpole looking things. And if you follow a fluid element in one of these simulations, what they find is that a fluid element experiences very violent density oscillations. You see it's got 5, 10, up to 20 millisecond time scale here, and the density in units of saturation density. For the first few milliseconds, things are absolutely crazy. Even after that, there's quite a lot of density oscillations being experienced by a little fluid element, carried along in this sort of maelstrom, this storm of the merger. It feels a lot of periodic compression with amplitudes that can be very big, and a typical period that looks like it's in the 1 millisecond range, so like a kilohertz density oscillations. So now the question we're going to ask is, how long would it take for bulk viscosity, and I'll be telling you what bulk viscosity is telling you about it, how long does it take for bulk viscosity to dissipate a sizable amount of the energy of a density oscillation? What's the damping time, tau sub zeta? And as always, we have that 20 millisecond time scale hovering above us. Can it damp density oscillations faster than 20 milliseconds or so? Because then it could influence what happens in the merger. So let's think about it. Just like we had a simple picture of a hot region and its thermal equilibration, let's think about a density oscillation. So you've got material of some density, and as this little fluid element, it's carried around, it experiences compression and rarefaction with some amplitude. So it's got an average density, it's got a density oscillation at some frequency, which we already think is going to be in the kilohertz range. So how do we think about the damping of this oscillation? Well, it's exactly the same as it was in broad outline, the same as it was for thermal conductivity. You ask how much energy is stored in the oscillation, and you divide by the rate at which that energy gets lost. So energy divided by rate of loss of energy, and is it happening faster than 20 milliseconds? So let's estimate these things. Here's our little oscillation. What's the energy stored in that oscillation? Well, like any sort of simple harmonic oscillation, the energy stored in it goes like the spring constant times the amplitude squared. So in this case, the spring constant is the nuclear incompressibility, and there's various factors here that arise from the definition of the nuclear incompressibility, but it's basically nuclear incompressibility times amplitude squared. And then we ask, what's the rate at which bulk viscosity, whatever that is, I haven't told you yet, but it's a thing that can be present. What's the rate at which it sucks energy out of that oscillation and turns it into something else, which actually is going to be heat, or it can create neutrinos, which may be heat if they're trapped and may escape. And so this also goes like the amplitude squared. You can get this out of ordinary linear hydrodynamics. This is sort of the definition of the bulk viscosity, actually, is that it comes into the expression for the energy loss in this way. So the damping time, the time it takes for this density oscillation to lose energy due to bulk viscosity, is how much energy is stored divided by how quickly does it leak out. And we get this expression. And again, it's sort of similar to the thermal conductivity one. You've got something on the top that tells you how much energy is stored in the oscillation, in this case an oscillation, and you've got something on the bottom that tells you how quickly it leaks out. So to calculate this damping time, we need the nuclear incompressibility, tells us how stiff the material is, how much energy is locked up in an oscillation, and that we get from the equation of state. And you need the bulk viscosity, and the bulk viscosity comes from beta equilibration of the proton fraction. So that's the thing I'm going to be telling you a bit more about as we go forward here. Again, I want to not save up important things for too late, but tell you them up front. So here are the results. I'm not showing it as an expression like I did with the thermal conductivity. I'm showing it to you as a contour plot. So here we have a contour plot of this damping time. We're in the neutrino transparent regime now. So we're assuming that the temperature is low enough so that neutrinos escape and don't have their own Fermi surface. And so this is really, this plot becomes not valid as you go towards the top end of it. But we've got temperature and MEV up the side, baryon density along the bottom, and these contours are telling you that, that equilibration time, that tau sub zeta, how long would it take for an oscillation to lose a considerable fraction of its energy through bulk viscosity. And we've chosen a particular equation of state. If you're interested in the astrophysics, here's some stuff about the equation of state. And we've chosen a 1 kilohertz oscillation frequency because that's what the merger simulations are showing us, you saw earlier, is the typical frequency of these sometimes quite violent density oscillations. So what we see here is, and we're looking, when do we get the density oscillations being damped by bulk viscosity on the 20 milliseconds or faster time scale? And if you look at these contours, here we've got 100 milliseconds, here we've got 50 milliseconds. So these two inner contours, this little region here, for this kind of matter, is where you expect damping that might be significant as far as merger dynamics goes, strong enough to affect the merger. So it's at temperatures around 3 MeV here, and densities not too high, you know, around a couple of times saturation density or lower. Details are going to depend on the equation of state. So I now want to explain a couple of features of this plot, because I just showed you the result. I didn't tell you where it comes from. So this time I'm going to show you the result and then explain some features of it and use that as a way of trying to illuminate some of the physics that goes into this. So here is this same plot. The damping time expression is here. And there are two features of it that I want to try and talk about. So one of them is if you sit at a given temperature and increase the density, what you see is the damping time for density oscillations gets longer. Right? These contours have pretty much a top to bottom pattern to them. So as you go from low density to high density at any temperature, you're going from faster equilibration to slower equilibration. Why is that? Well, the answer is pretty straightforwardly visible in the expression for the damping time for density oscillations. On the top here, we have the nuclear incompressibility and the density. And as you go up in density, the matter gets more incompressible. That's because of short distance repulsive interactions between the nucleons. So there's more energy locked up in density oscillations of high density matter than there is in density oscillations of low density matter. The bulk viscosity does get a bit higher too, but it doesn't grow nearly as fast. So the result is that in high density matter, the oscillations carry more density, more energy, so they take longer to damp out through bulk viscosity. And that's why these contours have a sort of top to bottom shape to them. So that one is simple. Let's look at the other direction in this. Let's imagine fixing ourselves at a particular density and tracking from low temperature matter at a given density up to hotter matter at that density. And what you see here is an interesting non-monotonic dependence on temperature, that at low temperatures at a given density, the damping is slow. Here we got the 10-second contour. As you go up in temperature, as you heat the material up, the damping time for density oscillations gets shorter. The bulk viscosity is getting stronger. But then if you heat it up too much, above about 3 MeV, the calculation is telling us, the bulk viscosity drops off again and the damping time gets longer again. So the damping is slow at low or high temperature, and there's a sort of just right temperature in the middle where the damping is fastest because the bulk viscosity is biggest. And it's because of this non-monotonic dependence of bulk viscosity on temperature. And that's what I'd like to explain a bit about right now. So why is there bulk viscosity? Let's get to the physics. The reason there's bulk viscosity is that when you compress nuclear matter, the proton fraction wants to change. The equilibrium proton fraction is not the same at all densities. That's basically because the protons and neutrons are different, are non-relativistic to a different degree. But that's a feature of all equations of state. So only weak interactions, though, can change the proton fraction. You know, if you want to change the proton fraction, you want to turn neutrons into protons or protons into neutrons. And in the neutrino transparent regime we're interested in, it's happening via these sorts of processes. Neutron goes to proton and electron, or electron capture on a proton. Okay, so why does this give you bulk viscosity? Well, if there's some property of a material, in this case the proton fraction, that is slow to equilibrate, then if you're doing a density oscillation, you can find that the density, in other words, the volume of a fluid element, gets out of phase with the applied pressure. And you can end up doing work in the course of one density oscillation period. So the dissipation, the energy that you lose if you're the mechanism that's making the oscillation happen, is the integral of PDV. It's just PDV work done on this fluid element. And if you want to integrate over a whole cycle, it's more convenient to express this in terms of a time integral, integrate over one period of the oscillation. So it's pressure times rate of change of volume integrated over time. So let's just see how that can end up being non-zero. So firstly, let's look at the case where there's no phase lag. There's no property of the material that takes time to equilibrate. In this case, pressure and volume have a nice, unique relationship. So when you increase the pressure, you decrease the volume. And when you decrease the pressure, you increase the volume. You go back and forth along this line. This is a perfect spring. This is a Hooke's law spring. Okay, this nice straight line here. So there's no phase lag and there's no dissipation. The integral of PDV here is 0 as you go back and forth along this line. And you can see it in terms of this expression here, that the pressure goes through one sinusoidal cycle. The volume, the dotted blue line, is 180 degrees out of phase with the pressure. When the pressure goes up, the volume goes down. When the pressure goes down, the volume goes up. And that means that dV dt, this thing here, is 90 degrees out of phase with the volume, because it's the time derivative of it. The volume is 180 degrees out of phase with the pressure, so dV dt is 90 degrees out of phase with the pressure. Integrate them, you get 0. Okay, something with itself and something 90 degrees out of phase, integrate 0. So no phase lag, no dissipation. Now suppose there is some phase lag. In this case, what you get is this hysteresis loop, where as you're compressing the material, increasing the pressure and decreasing the volume, it behaves slightly differently from when you're uncompressing it and the pressure's going down and the volume's going up. So it's a kind of memory effect that it remembers whether it was recently compressed or recently uncompressed. And that's comes from the delayed equilibration of some component of the material, in this case, the proton fraction, which equilibrates through the weak interaction. And you can see it again here in terms of this, that the pressure is doing its thing. The volume, the dashed blue line, is not 180 degrees out of phase with the pressure. The volume has a little phase shift to it. And the result is that dV dt here, 90 degrees out of phase with the volume, but not 90 degrees out of phase with the pressure. And so the integral is not 0. So the volume and pressure get out of phase, and you end up doing net work when you go through one cycle of compression and decompression. Okay,
The
now,
area of that loop is the work.
yes, that's right. The area of this loop is the work. Thank you. That's right. It's this integral of PdV. Now, we're trying to understand the non-monotonic temperature dependence of our damping time, which comes from the bulk viscosity. And I'm just going to kind of tell you about that and try and motivate it. So the bulk viscosity, it turns out, has a resonant form. If you look at the bulk viscosity as a function of the internal equilibration rate, there's an internal equilibration rate which tells you how quickly protons can turn into neutrons and vice versa. If you look at that equilibration rate and you vary that equilibration rate, then the bulk viscosity goes through a resonant maximum. At very slow equilibration, at very fast equilibration, there isn't much bulk viscosity. And in the middle, there's a big bulk viscosity. And that's when the internal equilibration rate, its time scale, matches the frequency of the oscillation that you're imposing on the material from the outside. So this is the resonant form. This is how it looks. And I'm just going to try and motivate it a little bit. So let's imagine the case where the internal equilibration is really fast. Okay? If the internal equilibration is very fast, you can turn protons into neutrons instantaneously, then the system is always in equilibrium. As you compress it, it's always in equilibrium every step of the way. As you uncompress it, it's always in equilibrium every step of the way. And that means that there's never any phase lag. It's always up to the minute. It's got the pressure it should have at that volume. So as the equilibration rate goes to infinity, we expect the bulk viscosity to go to 0 because there is no lag. There's no delay in equilibration. What about the opposite extreme? Supposing you've got proton fraction equilibrating very, very slowly. Well, if it equilibrates very slowly compared to the oscillation time, then it doesn't even try to equilibrate. When you compress and you uncompress, the proton number and the neutron number will both be separately conserved. There's effectively no way to turn protons into neutrons. Effectively, you have a new conserved quantity because you've turned off the equilibration of proton fraction. So again, the system is always in equilibrium. It's never trying to do anything different from what the state the compression brings it to naturally. So you compress it and you uncompress it, the proton fraction always stays the same. It doesn't try and equilibrate. So that, again, there's no phase lag between pressure and volume, and there's no bulk viscosity. So that's down here at the slow equilibration end. The maximum phase lag is when, as you're compressing it and uncompressing it, it's lagging behind on about the same time scale as the compression and uncompression that you're doing. So this, I hope, helps illuminate why the bulk viscosity is this funny non-monotonic function of temperature. It's got a resonant form because only when the internal equilibration timescale matches the externally imposed density oscillation, only then do you get a big bulk viscosity. And this equilibration rate is sensitive to the temperature because the temperature determines the amount of phase space available for those Urquhart processes that turn protons into neutrons and vice versa. So the beta equilibration rate gamma here is sensitive to the temperature. So as you scan up through temperature at a given density from low temperature to high temperature, you're going from slow equilibration of proton fraction to fast equilibration of proton fraction. Somewhere in the middle, that equilibration rate, that microscopic equilibration rate, matches the 1 kilohertz frequency of the oscillation you're doing. And at that point, you get maximum phase shift, maximum dissipation. And we can see that it's big enough that at low density and this temperature that hits the resonant maximum, it's fast enough to damp these density oscillations on the same time scale as the dynamics of the merger. So here's my summary, just about on time. So my summary is, okay, what we've concluded is some forms of dissipation are probably relevant physically for neutron star mergers. We looked first at thermal conductivity, and shear viscosity has a similar story behind it. If neutrinos are trapped and if there are sufficiently fine scale thermal gradients, then there's a chance that thermal conductivity could play an important role on the time scale of a merger. And then with bulk viscosity, we've seen that now in neutrino-transparent nuclear matter, so at lower temperatures, it looks as if the bulk viscosity is capable of damping density oscillations, and there certainly are density oscillations. We saw those in the simulation data. The bulk viscosity is capable of damping those sufficiently quickly that it would be relevant and have some impact on the evolution of that merger in its early stages of post-merger. So what sort of next steps are there? There are lots of next steps, but I'm just going to throw out a few of the obvious ones. So one thing is, it would be nice to include bulk viscosity in merger simulations. And there's different ways of doing this. You can put it in the fluid dynamics as a bulk viscosity term in the hydrodynamic equations that the merger simulation people solve. You can also do it more explicitly by tracking the proton fraction and keeping track of the processes that turn protons into neutrons, and then you're basically tracking an additional chemical potential, and then you get the PDV work done explicitly as sort of hydrodynamic PDV work. Another thing you can do is go beyond the matter that we looked at. So what I showed you here was results for ordinary neutron, proton, electron matter, but you can ask about hyperonic matter, pion condensates, nuclear pasta, quark matter. There's all sorts of different forms of matter. And we'd like to know, do these have significantly different bulk viscous damping or thermal conductive dissipation, which might give us ways of distinguishing their presence if we get enough merger data. The in-spiral is another intriguing place. Could there be bulk viscous damping of density oscillations in an in-spiral? And there's even beyond the standard model physics. So let me just have a couple of post-summary transparencies here. See, I cheated. So firstly, for hyperonic matter, we've got preliminary results from my postdoc, Alex Harbour. And this is the same contour plot of density of bulk viscous damping time in the temperature density plane, but it looks totally different this time. There's contours, there's still the resonant structure, but it looks completely different for hyperons. And that's basically because there's a hyperon onset at some medium density. And the final thing I want to show you is work done by my grad student, Stephen Harris, who's now about to start his postdoc at the INT, where he and collaborators looked at axion emission. So now we're beyond the standard model physics. And as a function of the axion coupling, they looked at the time for a hot region to cool by radiating axions. And they found that it's potentially possible for axions that are strongly coupled, but not, forbidden to not too strongly coupled. They can have interesting times, dissipation times to cool a region. So, okay, that's the end.
Well, thank you very much for a very nice presentation. We do have a number of questions, so let's start in the order they were raised. So first is Masood. Go ahead.
Thanks. Thanks for the very great presentation. I wanted to ask about one of your steps for WAR, and that is the simulation, including bulk viscosity in merger simulations. I have, from your talk and a little experience back in Frankfurt with Resonant's group, I have the guess that you need to include the bulk viscosity, but you also need to somehow assume that the rest mass density is not equilibrium one. I mean, you need to somehow use both, like for example, if you want to have a second order hydrodynamics, you need to assume an MI-like equation also for the mass rest density. And I think that, I don't know if you think your idea about if first order hydrodynamics works in this case, or we need to go to something like second order versions as we do in the heavy ion collisions.
Right. Yeah. I mean, there are issues with including bulk viscosity. You have to ensure things are still causal, and you have to have a separate sort of bulk viscous stress energy, which relaxes at that internal equilibration rate gamma. I believe it's known how to do this. So that's really more a question for the merger simulation fluid dynamics experts, but I believe they know how to do this.
Okay, thanks.
Okay, next question is from Efrain.
Thanks, Mark, for this very interesting talk. I only want you to comment a little more about quarks. That is, how do you expect that quark can change the results?
Well, there it depends. There's different phases of quark matter. So obviously, as Igor mentioned at the beginning, I've spent time studying superconducting phases of quark matter, and they can have quite high critical temperatures, according to the estimates based on NJL models and things like that. So it's quite possible that superfluidity and color superconductivity could be present if there's quark matter in this merger. It needn't be wiped out by the temperature. But the temperatures do get very high, so there could be a mixture of regions that have Cooper pairing of quarks and don't. They would have quite different heat capacities, depending on the gapping, different thermal conductivities, different bulk viscosities. Just among the quark matter phases, there could be quite a range.
Okay, thank you.
Okay, sorry, the next question is from Jamie Stafford.
Yeah, hi Mark, thanks for the nice pedagogical talk. It was very instructive. So my question is just about the EOS dependence on the damping time. So did you choose one that is supposed to be a good choice, or is there some dependence?
Okay, so let me go to my extra slides. Now let me see, which one was it that I wanted? Here we go. So this is the more like what occurs in our paper, where we studied two different equations of state. The one I showed you was this one, which is a stiffer one. We also did calculations for this softer one, and it has a slightly different set of contours, but they're not hugely different. So I didn't bother in the talk showing these side by side. But since you asked, we did at least look at two, one on the stiffer side, one on the softer side, to make sure that the thing wasn't radically changed by going to a different equation of state.
I see. Okay. And then do you think that the one you chose is a better choice for some reason? The one that you chose to talk about today?
No, I just chose it because the contours look a little simpler. And as you said, I was trying to be pedagogical. So I didn't want to get into questions of, why is there this little island here? And it's to do with details of the susceptibilities in this equation of state that have a non-monotonic behavior. But I just thought, let's choose the simpler one.
Okay, thank you very much.
Okay, next question from Debarati Chatterjee. You have to unmute yourself.
Okay. Hi, Mark. Nice to attend your talk after so long. Thanks to Igor for organizing this. So my question is, do you think the resonant behavior of bulk viscosity could be affected by the strong magnetic field in the merger scenario?
Yes, so I didn't put magnetic field down in here as another thing to look at. But of course I could have and probably should have. I don't know. Now, so the question is, would the magnetic field be strong enough to change these sorts of rates here? Where are we going now? Yeah, you're looking at the rates of these equilibration processes. And I think a magnetic field would have to be really quite strong. The sort of temperatures we're talking about, the Fermi surface is somewhat blurred. The magnetic field, I think, would have to be pretty strong to make a big difference to that. It might be more significant with thermal conductivity, maybe, if it's making it more difficult for, if charged particles are trying to curve. But then I guess the neutrinos don't care about the magnetic field, so maybe that's not such a big deal either. Just intuitively, I'm inclined to think the magnetic fields wouldn't change these microscopic properties so much. I'm inclined to think their main impact would be that they would change what happens in the simulation, the hydrodynamics, which bits of fluid are flowing where, how much shear is there, how much thermal gradient is there, how much density oscillation is there. I suspect those large scale things would be where the magnetic field would come in more than the microscopic things.
Okay, I was curious
that's my
because
guess. Yeah. Okay.
right, because magnetic fields do affect the sub and suprathermal regions, so I was curious.
Right.
Yeah.
Yeah. I mean, it's worth looking at. I'm just telling you my sort of instinctive reaction.
Mm-hmm.
Okay. Next question from Vivian and Sarah.
Great talk as always, Mark. Good to hear you. About the magnetic field, before I ask my question, I think probably you would see some anisotropies coming if you introduce a magnetic field. Anisotropies in some of the coefficients probably that come from the charged particles. And I don't know how important that would be. It depends on the magnitude of the field and other parameters, but that could be something, even in the neutrinos, you might have anisotropy because they get indirect through the interaction with the other particles, they can feel the magnetic field in that way. But my question is related to something else. Do you think that, I know that you're trying to introduce the transport properties as part of the simulations to be able to do a more accurate simulation of the merging process, but do you think that with this approach, you can also predict more accurate the outcome of the mergers and the properties of the entity, whether it's a neutron star, what are the properties of the matter in that neutron stars or not?
Well, yeah, we are really doing microscopic physics that we're offering as input to the simulation researchers. And it's very hard to kind of see through to how that will end up impacting the evolution of the merger. So I didn't speculate about that, and I don't think I know how to speculate about that. It's possible that some of these transport properties may have an impact on some specific aspects of the merger, but at the end of the day, they may not have much impact on the gravitational wave signal, or it's possible they do have some impact on the gravitational wave signal. And I just can't guess. You know, I don't feel like I can mentally shortcut a full GR magnetohydrodynamic simulation. So I'm hoping that people will try it. They'll put some transport properties into the simulations and we'll see.
Okay, the next question is from the chat room. It was from Henry de Jong.
Hello, Mark. Thank you very much for your talk. My question about gravitational wave signal was answered, but I have another one on these on the macro view that you're taking on this. What about the kilonova aspect? What effects might this have on the kilonova itself, and are you looking into that at all, or did you see anything on the last one that we had?
So again, the astrophysics of this is something that I don't feel very qualified to pronounce on. It is when you look at the we go back to what you see in this contour plot here is that the bulk viscosity does get stronger in regular nuclear matter down at low densities. And it's possible that there may be, I sort of stopped at nuclear saturation density in these plots. But it's possible that in the outer parts of the merger, where some of these interesting nuclear processes are happening that give you kilonova and things like that, it's possible that there may be important bulk viscosity effects happening out there that are kind of outside the range that we studied. So it is possible, but I haven't ventured into that territory.
Okay, thank you.
Okay, next question, Zidulin.
Thank you for the talk. It's very interesting. So now I know that your bulk viscosity might be very important for the neutron star merger. So could you please have some comments on the importance of the bulk viscosity on a neutron star? I mean, not a merger, but just for a single neutron star. Is that still important?
Okay, yeah. So well, yes. So so this is something I used to work on along with Kai Schwenzer and other people, and many people have worked on this. There are density oscillations, you know, sound waves, if you like, in isolated neutron stars. And the one that we looked at mostly was a thing called an R mode, which can be unstable, and it can get going. This vibration of the star can get going all on its own. And we looked at bulk viscous damping of R modes. And indeed, when you look at the R mode instability, you find that bulk viscosity and shear viscosity between them are the important things that damp R modes. So yes, bulk viscosity does come up in isolated neutron stars in a lower temperature regime.
Yeah, thanks. Yeah, I guess maybe I want to say a little things about the reason why I am asking these things. Because recently we find that the nuclear pasta might be able to give a very strong direct VUCA-like reactions. But the nuclear pasta is the structure of that nuclear pasta might be very sensitive to the temperature. So I'm not sure, because for the neutron star merger, the temperature might be a little too high for the pasta. So we are thinking if this pasta mechanism might be able to have some influence on the bulk viscosity for an isolated neutron star. But
yes.
Anyway, yeah, thank you so much.
That's a very interesting question. And that is the main way that one would imagine nuclear pasta playing a role. And it would be for things like R modes, you know, which are large amplitude, or at least potentially large amplitude density. They have a density oscillation component to them.
Yeah, okay, thank you so much.
Okay, next comment, I suppose, from Sanjay.
Hi, Mark. I just want to make a comment that, you know, we've discussed in the past. At low density and low temperature, the mechanism for changing neutrons to protons is what you discussed. But at higher densities, even as high as just nuclear density, and for relatively low temperatures of order 5 to 10 MeV, you can change neutrons into protons by emitting charged pions, and that is a strong interaction. So when those interactions come into play, the nature of bulk viscosity changes qualitatively. You have to now think about changing pion number, and pion number will drive bulk viscosity for densities greater than nuclear density and temperatures greater than about 10 MeV.
Right, I agree. So the presence of pions, I guess I wrote pion condensed here, but that's maybe writing it, that's a too specific phrase, because condensed, you know, can mean a low temperature coherent state, and that might not be what you have. But having a pion population, a thermal pion population in the star, could indeed have a very big influence, yes.
Right, and the crucial point is that you don't need temperatures of order the pion mass. You need very low temperatures because the difference between the neutron and proton energies is very large.
Right, yes, absolutely. So yes, I agree. I should rephrase this when I if I ever get to give this talk again, that yeah, the pion contribution or something like that is a very important thing to look at. I agree.
Okay, next question from Marnoush.
Thank you very much for your great talk. I indeed have a general question. You mentioned 3 dissipation transports, thermal conductivity, shear viscosity, and bulk viscosity. And you mentioned that they all have limited circumstances to damp the merger, as the dynamic is known to be damped. So if they won't do that, as well as we want to do, what will dissipate the merger like we expect to?
Well, so in the simulations that people do right now, none of this is included, right? There's no, none of these transport or dissipative processes are included. So what they have is other dissipation mechanisms, the emission of gravitational waves, the emission of neutrinos, since they're numerical calculations, they have some numerical viscosity in them, which of course isn't physical. So one, doesn't expect that to determine what happens. But yeah, there's mechanisms in the simulations that do some of this, and I'm just saying we should include all of them.
Okay, thanks.
Okay, I believe there is one more comment from George Naronia.
Yes, so thank Mark for this great talk. And it's just a comment about this issue regarding the inclusion of viscous effects in this general relativity simulation. So in fact, it's true that for a long time, it was hard to actually do this in practice because there were problems with causality and some other issues. But since, basically last year, this problem has been solved. So it is possible to do, in principle, these simulations of bulk viscosity. And even this year, also there are new developments regarding other viscous channels as well, like thermal conductivity and shear viscosity. So in principle, all the machinery is already ready. So someone has to implement that and see what it looks like.
Okay, let's see if we have, there is another comment. Masoud, go ahead.
I wanted to make a comment on George's comment, actually. I think that he's referring to their paper, and it's a very nice paper that prepare the thing that you actually have to do, but it seems that in practice, there are some problems that I don't know if there were progress about solving the equations. There were some divergences and things like that that happened in simple setups. That was the problem actually. But
okay.
Maybe we should
I just wanted to have a very specific proposal to you, Masoud and George, that you will probably start a new collaboration as a result of this. So you will have to acknowledge Mark's talk if you do.
Sure. We have talked to George about that.
Okay, actually, I sort of had one question myself, but I think maybe I'll skip it because it was almost answered. Maybe if you could say it briefly in 2 words. The thing is that in your executive summary, you kind of suggested that the bulk viscosity and heat conductivity are sort of similar in some, it was shear. It was shear.
Oh, yes.
Yeah, so I actually...
Thermal and shear are sort of end up having roughly the same looking.
Anyway, but concerning the question, it seems like the heat conductivity and shear, for that matter, will be primarily big and important in large temperature regime, well, definitely above 5 MeV or so. The bulk viscosity, on the other hand, is only concentrated in that relatively narrow range of temperatures. So it seems like for the simulations, it's not really that the bulk viscosity will be critical since it has such a narrow range of temperatures. Would you?
Well, yeah. So different transport or dissipation mechanisms will be relevant in different parts of the merger. So there'll be some parts where the neutrinos are trapped, and maybe thermal conductivity via neutrinos will be important if there are fine enough gradients. Maybe other regions will have significant bulk viscosity. But yeah, I'm not making a statement about everywhere in the merger. No.
Right. Well, the diagram you quoted from Matthias was actually sort of showing the temperatures primarily mostly above 5 MeV.
Right. So yeah, so I agree. So if you go back and you look at that, let's go all the way back and see if we can get there. Yeah, so if you look at this, actually, yeah, you see that there is, according to this simulation, there isn't that much sitting at around this low density and 3 MeV temperature, right? So that's why I think it's valuable to look at this in different simulations with different equations of state. Yeah, it all depends how much of the star looks, it has in it the conditions where bulk viscosity is maximal. And I agree, if you look at this this simulation with this equation of state, there isn't much of the star in the maximal bulk viscosity regime of density and temperature. That's true.
Okay. Just for clarification. I don't believe we have other people wanting to ask questions. Please correct me if I'm wrong. I don't think I missed anything in the chat room. I don't think I see any hands raised. So if there are no more questions, I would like to use this opportunity to thank Mark for taking time preparing a very nice and clear presentation. I truly enjoyed every moment of it. I see claps in the chat, so I'll vocalize that symbol, and I guess we will be ending here.